to this session on electrochemical honing, electrochemical grinding and some other variant processes in the electrochemical machining systems under the course Advanced Manufacturing Processes. In the previous two sessions, we have discussed about the basics of electrochemical machining process, its working principles and its subsystems. The advantages, limitations and applications of the ECM process have also been discussed. In the present session, we will study about some other variant processes of the basic ECM process. These include electrochemical grinding process, also in short is known as ECG process, which is a combination of electrochemical and conventional grinding process. Then electrochemical honing, in short ECH process, which is again a combination of the basic electrochemical process as well as the conventional mechanical honing process, and two other variants like ECDE, electrochemical deburring process, and STEM process. Let us first discuss the electrochemical grinding process. Electrochemical grinding or ECG is a variant process of the basic ECM. It is a bar free and stress free material removal process, wherein material removal of the electronically conductive material takes place through the combined action of mechanical, which is nothing but conventional grinding process, in which the tiny chips will be removed through scratching, and electrochemical process, in which material will be removed through electrolysis, as we have already discussed during the ECM process. In this process, the abrasive leaden grinding wheel is connected to the cathode and the workpiece is connected to the anode. They are separated by an electrolyte fluid. The fine chips of the material that is removed from the workpiece, which are also called debris, stays in the electrolyte fluid, which is further filtered out. Electrochemical grinding and electrochemical machining are similar processes, with a difference that a wheel substitutes the tool used in ECM. The wheel shape is similar to the desired work shape. Now, let us see the process of grinding in ECM. The main feature of electrochemical grinding is the use of a metallic grinding wheel, which is embedded with insulating abrasive particles such as diamond. The abrasive particles are set in the conducting material. Copper, brass and nickel are the most commonly used materials, while aluminum oxide is a typical abrasive used while grinding steels. The commutator is an electrolytic spindle having carbon brasses and holds the grinding wheel. It receives a negative charge from the DC power supply and the workpiece is connected to the positive terminal. In the ECG process, the grinding wheel slightly touches the workpiece and electrolyte is supplied onto the grinding wheel near the workpiece. The wheel carries the electrolyte through the grinding process. It thereby results in an electrochemical action. A nozzle similar to the one which carries coolant in a conventional grinding process is provided. The nozzle enables the flow of the electrolyte fluid to the work tool contact area. The electrolyte along with will work simultaneously in the process of cutting. The electrochemical cells thus formed further oxidize the surface of the workpiece. The wheel carries away the formed oxides, thereby exposing the fresh metal layers beneath the oxide layer. In this process, the major material removal activity takes place by the electrolytic action, which is around 90%. The rest of the material removal, around 10%, takes place due to the mechanical grinding action. The pressure applied on the grinding wheel is, however, much lesser than the conventional grinding process. Thus, the basic necessity of frequent wheel dressing and truing, as in the case of conventional grinding process, is also eliminated. The basic mechanism can be explained something like this. This is the workpiece, which will be connected to, as we have already said, to the positive terminal of the supply. Here the other terminal will consist of the grinding wheel. So, this is the grinding wheel, this will be connected to negative terminal, or this will form the cathode. Here in between there will be a nozzle which will supply electrolyte. This is nozzle for electrolyte supply. Therefore, there will be a continuous supply of electrolyte here, and thereby it forms a basic ECM cell, electrochemical machining cell, in which there will be a tool which will be connected to the cathode. This is the cathode, and the workpiece, which should be of course electrically conductive, and this will be connected to the anode of the power supply. Now, they will be separated in between by the electrolyte. So, this is nothing but the electrolyte, and these are like conventionally used electrolytes as per the material specification or the material to be machined. Now, this grinding wheel, as we know, this will consist of generally two phases. One phase will be of the binders, and onto these binders there will be abrasive particles embedded on this. These abrasive particles actually will be responsible for scratching the workpiece like this. So, these abrasive particles in fact will take part in taking some materials away from this workpiece surface. So, this is the workpiece, and this will take away some tiny chips from this. So, these are tiny chips, also we can call as debris. These tiny chips, this will be rotating like this, this will be rotating like this. Now, this matrix part or the binder part will be metallic material, and therefore, they are conductive. However, these abrasive parts, these are abrasives, these are abrasives and they are generally non-conductive. Thus, due to this presence of these abrasives in the cutting zone. So, this is, if we consider this as the cutting zone. So, the direct contact between the anode and the cathode will be prevented due to the abrasives which are non-conductive in nature. So, this, as we have already told, this will be connected to the cathode and this will be connected to the anode, and the direct contact between this cathode and the anode will be prevented by this abrasive particles, which will take part in abrasive actions, and these abrasives will be responsible for machining only 10% of the total 10% of total material removal. Whereas 90% of the material removal, of the total material removal, will be through the conventional ECM process. So, here in the screen also it is shown a schematic of the electrochemical grinding process, in which this is the workpiece to be machined, which is connected to the positive terminal of the power supply, DC power supply, and the other wheel, the other terminal is connected to the wheel, the grinding wheel, which will act as the cathode, and there will be some brush arrangement here, some brush arrangements here, commutator arrangement, which will prevent the direct contact with the electrical connections to the machine body. And as we have already explained, so there will be a nozzle which will supply the electrolyte through this nozzle to the machining zone. So, here this will be the machining zone in which the distance between the cathode as well as the anode will be minimal, and there the actual electrolysis will take place. And then in addition to that, as we have already discussed, there will be the mechanical scratching action which will be responsible for removing some of the materials in the form of tiny chips. Moreover, another important thing in this is, as we have already discussed, there will be a gas layer formation or oxide layer formation on the workpiece surface. So, if this is the workpiece, then if this is being ground, this is the workpiece. So, this is connected to negative and this is connected to the positive terminals. Now, during machining there will be an extremely small oxide layer formation because of the electrolysis action. Now, this is the oxide layer, and this oxide layer prevents or minimizes the electrochemical action further. Therefore, in ECG process, because of this grinding action, this grinding small scratching, this grinding abrasives, they removes this oxide layer and it revitalizes the electrochemical action, thereby the continuation of this electrolysis process takes place, otherwise it slows down. Moreover, one more phenomena is, as we have seen earlier, there will be the hydrogen gas evolution. Now, this hydrogen layer also acts as the passivating agent. So, this causes passivation in the material removal process. Now, because of this scratching action of this abrasives, scratching action of the abrasive, the gas layer as well as the oxide layer get removed, which enhances, results in, or we can say this results in higher MRR in this process, or we can say this results in better process performance. Now, let us look at the process characteristics in this process. The life of a grinding wheel in electrochemical grinding process is very high, as approximately 90% of the material is removed by electrolysis action and only 10% is due to the abrasive action of the grinding wheel, unlike in the conventional grinding process where 100% of the material removal is due to the grinding or abrasive action of the grinding wheel. The ECG process is capable of producing very smooth and bar free edges, unlike those formed during the conventional grinding process. The heat produced in the ECG process is much less, leading to lesser distortion of the workpiece. This also we have seen in the conventional grinding process, many cases there will be grinding burn because of the very high heat developed in the cutting zone and because of low conduction and convection of the heat from the cutting zone. Therefore, this is an associated problem with conventional grinding process. However, in this process the workpiece will be always wet with the electrolyte system and most of the material removal will take place, which we have already stated as 90% through electrical disassociation. Only 10% of the total material removal will be through the grinding process. Therefore, the thermal damage due to this grinding temperature development will be much lesser relative to the conventional grinding process. There is very little tool and workpiece contact and hence the process is ideally suited for grinding the following. Number 1, fragile workpieces which are otherwise very difficult to grind by the conventional processes. The parts that cannot withstand thermal damages, as we have already spoken about, the damages due to the thermal or the temperature development during the grinding process is minimal here in this process, and therefore, those parts which are likely to be damaged because of the heat of machining can be machined in this process. The parts designed for stress and bar free applications can be very easily and very effectively machined by this process. Now, let us see few applications of this electrochemical grinding process. So, they include the following: in production of tungsten carbide cutting tools, this ECG process is found to be very effective in production of bar free sharpening of hypodermic needles, in grinding of superalloy turbine blades, in form grinding of aerospace honeycomb metals, in removal of fatigue cracks from steel structures that have been used for underwater applications. The ECG process can be applied to the following common methods of grinding. Number 1, face wheel grinding. Number 2, cone wheel grinding. Number 3, peripheral or surface grinding. Number 4, form wheel or square grinding. Now, let us move on to another process which is also considered as a variant of this basic electrochemical process, which is nothing but electrochemical honing process. The principle is almost similar. As we know, in the basic honing process there will be generally internal surfaces will be machined. So, if this is the workpiece, cylindrical workpiece, and these are the internal surfaces to be honed, internal surfaces. Then what is being done is there will be one hone which will be used for finishing this. This hone will have some small or tiny abrasives embedded into this abrasives, and these abrasives will be responsible for touching the workpiece material. So, this is, if this is the workpiece surface, this hone, the abrasives embedded on this hone will touch this surface and they will remove tiny chips from the workpiece surfaces, making this internal surface highly finished. This is the surface to be finished, and after this is, so this is called honing stone. Honing stone. This honing stone moves in two different directions. One is there will be a rotary motion of this honing stone, and there will be one reciprocating motion about this axis. Therefore, the resulting movement of the honing stone or the parts of this abrasives that will move with respect to the surface to be finished will be something like this. This is also called cross hatch pattern. This is considered to be a characteristic lay pattern obtained in honing. This is found to be very useful, as these cross sections here, they serve as tiny pockets where fluids can be retained in some applications. For some applications. Thus, this particular process is considered to be very useful for creating some functional surfaces. Now, in this hybrid method that we are currently talking about, in addition to this basic honing process, these workpiece and this honing stone will be connected to the anode and the cathode respectively, and thereby a basic ECM cell will be constructed, which will be responsible for removing some material with the basic electrochemical action that we have already discussed. So, honing is a basic finishing process, so in which the tool reciprocates as well as rotates at a very low speed, as we have already explained. Due to this reciprocating and rotating action, fine tool marks are produced in the shape of a helix that we have already discussed. These fine helical marks, also known as cross hatch tool marks, act as the oil carriers and oil retainers. This is a very important feature required for hydraulic applications, wherein this retained oil helps in self lubrication of the cells and internal parts. Honing process uses a continuous circulating oil, commonly called the honing oil. This oil helps in heat removal and also carries away the powdered sludge formed by the removal of material from the workpiece. Conventional honing is a mechanical process which uses fine abrasives such as silicon carbide, boron carbide or diamond. These fine abrasives are embedded by powder metallurgy technique in the required shapes. These are further attached to the honing mandrel. They are often called as honing stones or honing sticks. Just now we have discussed about these honing stones. The electrochemical honing process, which is a hybrid process integrating the basic electrochemical machining action and the mechanical honing action, in which the material removal takes place by the conventional and well known shearing action, yields added benefits in terms of number 1, improved surface finish, number 2, reduced work time, and number 3, improved tool life, which is found to be up to 3 times the basic process. By passing electric current into the electrolyte solution, major material removal takes place by the electrolytic action, as we have seen in case of electrochemical grinding, in which 90% of the material removal takes place in the form of electrolytic action, whereas only 10% is through basic grinding action. So, here also it is similar. The basic electrolytic action is the major material removal mechanism in this process as well. And the honing stones or abrasives help in removal of the material by very small percentage, which is approximately 10% in this case as well. Let us see the principles of electrochemical honing process. In this process, as we have already indicated, the material removal occurs by anodic dissolution followed by mechanical abrasion of the abrasive grains that are bonded to the honing stone. The cathodic tool is similar to the conventional honing tool with several small holes for electrolyte supply into the inter-electrode gap. As we have already told, if this is the workpiece surface and this is the honing stone, in which these small these are the abrasives. So, this will be considered as inter-electrode gap. This is also known as IEZ. This is nothing but inter-electrode electrode gap. This will keep the positively connected workpiece and negatively connected tool, which is nothing but the honing stone in this case, apart by this distance of this IEZ, and in between there will be the abrasives which will actually make contact with the workpiece. So, this is the workpiece which is generally conductive in nature, and in this gap there will be the electrolyte kept on flown. So, this will be nothing but the electrolyte. Thus, as we can correlate with the previous basic ECM cell, so this has got the every characteristic of an ECM cell in which workpiece is the anode and the tool is the cathode, and in between them an electrolyte is being flown, keeping a distance between them is the IEZ or inter-electrode gap. So, here again the material removal will be 90% through ECM and only 10% will be through mechanical abrasion, which is nothing but honing action, The electrolyte provides electrons through the ionization process, acts as a coolant and flushes away chips that are sheared off by mechanical abrasion, in short known as MA, and metal sludge that results from electrochemical dissolution action. The majority of material is removed by the ECD or electrochemical dissolution phase, while the abrading stones remove enough metal to generate a round, straight and geometrically through cylinder. During machining, the mechanical abrasion removes the surface oxides. This we have already discussed with respect to the electrochemical grinding process, wherein also there will be an oxide layer, and this oxide layer will be removed continuously by the grinding action of the tiny abrasive present on the wheel. So, here also the same oxide will be removed by the tiny abrasives embedded on the honing stone. The removal of such oxides enhances the ECD phase and it presents a fresh surface for further electrolytic dissolution. As we have told, if this oxide layer forms, then the performance of the electrolytic dissolution comes down because most of the oxides are non-conductive in nature, and this stops the electrolytic tends to stop the electrolytic action, which however will be removed by this abrasive action of this honing stone. Sodium nitrate solution with a concentration of 240 gram per liter is used in this process instead of more corrosive sodium chloride or acid electrolytes. An electrolyte temperature of 38 degrees Celsius and pressure of 100 kilopascal and a flow rate of 95 liters per minute can be used for this process. Electrochemical honing employs direct current at a gap voltage of 6 to 30 volts, which ensures a current density of 465 amperes per square centimeter, which is considered to be quite high. Improper electrolyte distribution in the machining gap may lead to geometrical errors in the produced bore. Now, let us see what are the process requirements in electrochemical honing. In this process, the bonding material of the honing stones must be electrically conducting. This we have discussed with reference to electrochemical grinding process as well, in which the grinding will consist of metallic materials. That means, the basic binder phase consists of the metallic materials which are naturally electrically conductive. Onto these conductive materials, non-conductive abrasives like diamond or silicon carbide etc., are embedded. In cases where the honing stones are made of non-conducting bonding material, current is passed to the workpiece through electrodes mounted between the honing stones and the process is carried out. A small gap of around 100 microns is maintained between the work and the electrodes. The supply of electrolyte is made through a series of holes. Different electrolytes depending on the work material can be used. Material removal rate of 3 to 5 times faster than that of conventional honing and 4 times faster than internal cylindrical grinding can be obtained in this process. Tolerances in the range of plus minus 0.003 millimeter are easily achievable, while surface roughness in the range of 0.2 to 0.8 millimeter of average roughness are easily available. For hydraulic applications where the cross hatch pattern is explained earlier for oil retention is desired, then the electric current is turned off for the last few strokes and mechanical abrasion mode of honing is accomplished. However, for stress free surfaces and geometrically accurate bores, the last few seconds of mechanical abrasion should be avoided in favor of pure electrochemical dissolution process. Therefore, the marks or what we call as cross hatch pattern will be absent. Now, let us see few applications of the electrochemical honing process. The process markedly reduces the errors in roundness through the rotary motion. Moreover, through tool reciprocation, both taper and waviness errors are also reduced. Due to the light stone pressure used, heat distortion is also avoided. The electrochemical honing process is commonly used in precision finishing of various mechanical and hydraulic application oriented compounds like micro finishing of gears, micro finishing of pump and valve components. The presence of the electrochemical dissolution phase introduces no stress and automatically deburs the part in this process. The electrochemical honing process thus can be used for hard and conductive materials that are susceptible to heat and distortion. The process can tackle pinion gears of high alloy steel as well as holes in cast iron steel components. Hone forming is another application that combines the honing and electro deposition process. It is used to simultaneously abrade the work surface and deposit metal. The method is reversal of electrochemical honing in basic principles. Now, let us move on to other electrochemical machining variant processes and their applications. One such process is electrochemical deburring, which is in short known as ECDE. This process is used for removing bars from the inaccessible and intricate areas wherein conventional methods are non-effective. This process involves the use of flowing electrolyte for conducting electric current for the electrochemical reaction to take place. Based on experimentations and experience, the current and time of devouring are set. The commonly used electrolytes are sodium nitrate or sodium chloride. The devouring machines need to be built from non-corrosive materials, else the corrosive nature of electrolyte, which we have already discussed as sodium chloride and sodium nitrate, in which sodium chloride is highly corrosive as we know. So, this type of electrolyte will corrode the machine parts themselves. The basic applications of electrochemical devouring processes include hydraulics, where the presence of bars can affect the internal moving parts and damage seals of contaminate the oil, damage the seals, and therefore, if the seals are broken, then that will contaminate the entire oil. In aerospace or automobile applications for components like gears, manifolds, fuel supply components, etc., this process is used. Other applications involve consumer appliances and biomedical systems. The system gives higher reliability, lesser operational time, uniformity, and overall a very economical process. The process can also be automated very easily. The advantages of this process include increased MRR, bar free surfaces, reduced noise, increased accuracy, and reduced work damage. Now, let us look at another variant process, which is called shaped tube electrolytic machining, in short STEM process. It is based on the dissolution process when an electric potential difference is imposed between the anodic workpiece and a cathodic tool. Due to the presence of electric field, the electrolyte, often sulfuric acid H2SO4 is used, causes the anode surface to be removed. After the metal ions are dissolved in the solution, they are removed by the electrolyte flow. The tool is a conducting cylinder with an insulating coating on the outside. The tool is moved towards the workpiece at a certain feed rate, while a voltage is applied across the machining gap. In this way, a cylindrically shaped hole is obtained. STEM is a modified variation of the ECM process that uses acid electrolytes, for example, sulfuric acid. Let us quickly look at the process capabilities of this STEM process. Hole sizes of 0.5 to 6 mm diameter at an aspect ratio of 150, which is quite high, can be produced. Then hole tolerances obtainable in this process is plus minus 0.1 mm. Hole depth can be obtained as 0.05 mm. This is the tolerance as far as the hole depth is concerned, which is quite high. This process is limited to drilling holes in stainless steel or other corrosion resistant materials in jet engines and gas turbine parts, such as turbine blade cooling holes, fuel nozzles, any holes where EDM recast is undesirable. This recast layer can be removed by this process. drilling oil passages in bearings, etc. The advantages of this STEM process include the depth to diameter ratio can be as high as 300. A large number of holes, say up to 200, can be drilled in the same run. Blind holes and non-parallel holes can be drilled. No recast layer or metallurgical defects are produced. The limitations of this process include the process is used for corrosion resistant metals. This is also a very slow process. If a single hole is to be drilled, then the process could be hazardous. It can produce hazardous waste, and therefore, the special workplace and environment is required. Then the complex machining and tooling are required for this process. Another process in this electrochemical machining variants include the electrochemical jet drilling process. It is mainly used for fine hole drilling at a diameter to depth ratio of 1:1.12, which is lower than that obtained by capillary or ES drilling. The process does not require the entry tool as in case of ES drilling. It avoids use of fragile tooling. The jet of a dilute acid electrolyte causes dissolution and enough room is required for the electrolyte to exit, preferably in spray form. A typical high voltage of 400 to 800 volt is used in this process. The hole produced depends on electrolyte throwing power. The holes produced are about 4 times the diameter of the jet. Tapers are about 5 to 10% of the included angles. The lower limit of the hole size is determined by the lowest diameter of drills that could be drilled in the cathodic nozzle. Now, let us summarize what we have discussed in this session. In this session, we have discussed about the setup and important features of the electrochemical grinding process as well as the electrochemical honing process. Other processes like electrochemical deburring process, STEM process, etc., have also been studied in brief. Unique advantages, limitations, and applications of all these processes have been discussed. We hope this session was informative and interesting. Thank you.